Isn't it strange that humanity has created advanced technology, but we do not know why it behaves the way that it does? Even Einstein was disturbed by the quantum world, therefore he called it spooky action at a distance. This is the power of quantum computing. But modern scientists like Brian Cox admit we are forced to accept that the behavior of the universe at the quantum level is strange, counterintuitive, and apparently impossible. So the big question facing humanity is what godlike, impossible powers will quantum computing unlock in the future? In 100 years, 12 exascale quantum computers will create a complete simulation of humanity, and so 100 machines will simulate the entire observable universe and everything in it. This is the potential of quantum computers. Because while classical computers simulate the physical world, such as cars and planes in wind tunnels or buildings during earthquakes, quantum computers simulate the quantum realm itself, where atoms and molecules interact. This is what happens when humans build computers that harness the laws of quantum mechanics. We will see quantum computers break modern encryption, weather systems predicted with accuracy, and the simulation of molecular structures leading to new materials and medicine. This is the world of quantum computing. But let's go deeper. When quantum computers can map every neuron in the brain, humanity will simulate an entire mind. But preserving the true nature of consciousness is what stands between us and digital immortality. Or how about archaeologists reconstructing lost ancient civilizations, using quantum computers to analyze the subatomic information preserved in archaeological remains? Because deep within the atomic structure, quantum machines will decode previously invisible molecular patterns, therefore letting humanity replay history at the molecular level. And quantum machines will look out into the cosmos, predicting where else consciousness might emerge. The machines will model chemical and physical conditions needed for life, predict the chemical composition of distant exoplanets by simulating their atmospheric interactions, and model evolutionary pathways, the development of intelligence, resource availability, and technological advancement patterns, searching for the formation and evolution of alien civilizations. Humanity will map the likelihood of intelligence across the universe. But what about going back in time, all the way back to the beginning of time itself? Particle-level simulations will reveal what happened in the first trillionth of a second after the Big Bang, when space itself experienced exponential inflation. So humanity will finally understand how this rapid expansion created the quantum fluctuations that grew into today's galaxies and cosmic structures. But there is one more big question to ask these quantum machines. Please model the universe's eventual fate, showing us whether it ends in a big freeze expanding forever, or maybe, against all odds, it reverses into a big crunch. When quantum computers become mainstream, they will rewrite the rules of our understanding of reality and reveal hidden layers of our universe. Humanity will no longer be bound by classical physics, but will journey into the quantum realm itself. This is the next phase in computing evolution, and it all comes down to quantum bits. So the first thing to know is that qubits are the fundamental building blocks of a quantum computer. Classical computer bits are binary, either 0 or 1. Qubits can exist in multiple states, thanks to a principle called superposition. It is like a spinning coin. While a normal computer bit is the coin lying flat, showing either heads or tails, a qubit is the coin while it's spinning, existing in all possible states at once. But here is the problem. These quantum states are incredibly fragile. Quantum computers must be cooled to near absolute zero, colder than the void of space. Also, qubits are interconnected through a phenomenon known as entanglement. This is what Einstein referred to as spooky action at a distance. Now, imagine two synchronized human dancers. When one starts spinning clockwise, the other then spins counterclockwise. But entangled qubits are even stranger, as their synchronized dance happens instantly no matter how far apart they are, and faster than light itself could travel between them. More on that later. So quantum entanglement is real. Einstein never got to see this proven, even arguing against interpretations of quantum mechanics, believing the theory was incomplete. because such instant, faster-than-light correlations should be impossible. This interconnectivity, entanglement, is what allows quantum computers to explore millions and billions of calculations. But how are entangled particles created? And if this faster-than-light connectivity is able to occur in a quantum computer, then why can't it be used for instant, faster-than-light space communication, say between Earth and Mars? So to create entangled qubits in quantum computers, scientists use precise lasers and electromagnetic fields. You bring two particles, like electrons or photons, extremely close together under very controlled conditions. And when they are manipulated in just the right way, they become entangled. Their quantum states become linked. As for why we can't use it for faster-than-light communication, this is a common question. The key limitation is what's called the no communication theorem. So the problem is the spin direction of either particle cannot be chosen or controlled. If Earth and Mars each have one particle from an entangled pair, when either of the planets measures the particle, something strange happens. First, Earth and Mars have one particle from an entangled pair. They are spinning in all directions at once. The moment Mars measures their particle, this forces the particle to instantly choose a specific, random direction. Earth's particle becomes the opposite spin. The spooky part is that the particles affect each other instantly. But Mars can't force their particle to spin a certain way, which would allow them to send a specific message. And lastly, once either side measures their particle, the entanglement is destroyed, like a spinning coin that falls flat on one side. That is why Albert Einstein said, "I like to think that the moon is there, even if I'm not looking at it." This was Einstein's criticism of the idea that reality only exists when we observe it. It is when the particles are being watched that they are forced to pick a spin direction. The act of measuring itself affects the system. This is one of quantum mechanics' deepest mysteries. It is as if reality itself only becomes definite when it interacts with an observer, like a video game that only renders what the player is looking at. We truly don't know why measurement causes quantum states to collapse. This same mysterious collapse happens inside quantum computers. Humanity has created advanced technology, yet cannot explain why it behaves this way. But if the entangled particles are destroyed and collapse when measured, then how do quantum computers use them? Quantum computers maintain their qubits in superposition and entanglement, only measuring them at the very end of a calculation, keeping all the coins spinning until the final moment. Once you look at them, they collapse into one of their basis states, which are then interpreted as classical bits, zeros and ones. Each qubit is incredibly sensitive and needs to be kept in its delicate quantum state throughout the computation, which is why quantum computers require such extreme conditions of near absolute zero temperatures and perfect isolation. The slightest change in temperature, electromagnetic waves, or even cosmic rays can cause them to lose their quantum state, a problem known as decoherence. When the calculation is complete, only then are they measured, giving us the answer. The more success the quantum theory has, the sillier it looks. This was Albert Einstein's frustration with quantum mechanics, despite its accurate predictions. Quantum mechanics is the physics that describes nature at the smallest scales of energy levels of atoms and subatomic particles. Quantum computers are a type of technology that uses the principles of quantum mechanics, such as superposition and entanglement, to perform computations. Even with today's advancements, Einstein's words still ring true, but in a different way. Quantum mechanics has only gotten sillier, stranger, and more counterintuitive. Humanity's deeper understanding has revealed even more bizarre quantum phenomena. But unlike Einstein's time, we now know that this silliness is a fundamental feature of reality, not a flaw in our understanding. Einstein would likely marvel at how fundamentally strange and counterintuitive the quantum world remains. And what would he think about teleportation? Quantum teleportation was first successfully demonstrated in 1997. Teleportation transmits the exact state of a particle to another location. Scientists scan and measure an original particle, transmit that data classically at only light speed, and use quantum entangled particles at both locations to recreate it at the destination. The original particle is destroyed in the process of reading its quantum state, and its perfect twin appears at the destination, identical down to the quantum level. It is like sending a blueprint down to the atomic level of the object through a quantum fax machine. But if scanning for teleportation is destructive, as in the original quantum state is destroyed during measurement, and you can't read it without collapsing it, could this suggest something about death itself? What happens to the quantum information in our brains when we die? Could death itself be a kind of measurement where our quantum states are read and preserved in higher dimensions in string theory? When a quantum state collapses, whether in a quantum computer, during teleportation, or perhaps during death, that information might not be lost, but rather redistributed through higher dimensions. It is as if the information becomes entangled with the fabric of space-time itself, possibly tying together quantum mechanics to the theories of consciousness and death. Some theorists even propose consciousness might exist partially in these higher dimensions, that consciousness itself may be quantum in nature, and our brains are organic quantum computers, which could explain why it's so hard to pin down consciousness in purely physical terms. The quantum states in our brains might be interacting with these extra dimensions in ways our current science cannot measure. The quantum world might be stranger than we can imagine, and even the universe operates on quantum principles. So in the future, quantum computers will simulate the interactions between galaxies to the physics inside black holes, and by mapping the gravitational dance of every star, planet, and asteroid in our galaxy, humanity will master the three-body problem. That means the most efficient trajectories through gravitational fields can be calculated, optimizing spacecraft routes through the solar system. Now looking further out, deep space quantum sensors will detect microscopic distortions in space-time, revealing information of possible hidden wormholes. And even further out in the cosmos, quantum computers will simulate conditions at the edge of the observable universe, revealing whether space continues infinitely or curves back on itself in higher dimensions. Humanity will finally know if our universe is finite or infinite, flat or curved. And what about when space and time themselves break down? Quantum systems will reveal if the extreme conditions inside black holes could spawn new universes, with each black hole in our cosmos being the Big Bang of another universe. This could show us if reality is fractal, with universes endlessly creating new universes. Back on Earth, quantum computers will merge with artificial intelligence, and that means humanity's understanding of chemistry will be revolutionized as quantum systems simulate atomic interactions, leading to new materials with seemingly magical properties, such as self-healing metals, programmable matter, and metamaterials. But what kind of magical properties will be invented? How about phase-shifting metamaterials that alter their molecular structure on command, becoming completely rigid or fluid at will? Or what about self-assembling nanomaterials that grow into complex structures by following molecular blueprints, like DNA, but for inorganic matter? And at the same time, quantum metamaterials will manipulate and redirect light at the atomic scale, creating optical camouflage. This is also known as an invisibility cloak. But the first things we will see when quantum computers become powerful will be the mapping of every protein fold and molecular interaction in the human body, accelerating drug discovery. Personalized medicine will emerge that can predict exactly how an individual will respond to any treatment. These same simulations will reveal the secrets of photosynthesis, leading to biotechnological solar cells that capture energy as efficiently as nature. And then, quantum sensors will detect subtle changes in gravity, revolutionizing everything from mineral exploration to early earthquake detection. So quantum computer-enhanced AIs will discover new laws of physics by recognizing patterns in subatomic scientific measurements that human minds cannot comprehend. But quantum computing poses existential risks. Powerful machines will be able to break the RSA encryption that secures today's internet. every intercepted encrypted message ever sent in the past could be retroactively decrypted. Therefore, the entire digital security infrastructure of our civilization will be rebuilt. But quantum machines also pave the way for creating quantum encryption, such as key distribution. This has sparked a new arms race in cryptography, using the principles of quantum mechanics themselves to create unbreakable encryption, where any attempt to intercept quantum encrypted messages automatically destroys them. It self-destructs. So now the quest for quantum computing supremacy is reshaping geopolitics. Nations that master quantum technology first will have overpowering advantages in cybersecurity, drug discovery, financial modeling, and military technology. But there is one more big question. In the future, humanity will replay the first moments after the Big Bang. But will it reveal if the Big Bang was truly the beginning? Or did our universe emerge from the collapse of a previous universe? Will humanity see if time itself is cyclical on the grandest scales, with universes endlessly being born and dying? And if all particles in the universe were once entangled during the Big Bang, then could everything in the universe, including humans, at one point have shared a primordial quantum connection? The first and second volumes of the Encyclopedia of the Future are available on Patreon.